I wanted to make sure we're all on the same page with the definition of rational numbers. So a rational number, here's the definition, is a number that can be written in the form a over b, where b is non-zero, a and b are both integers, and a and b have no common factors. So a and b share no common factors. Okay, so a rational number, again, is any number that can be written in the form a divided by b. B is non-zero, a and b are both integers, and a and b share no common factors. So for example, 2 is rational because it can be written as 2 over 1. 2 and 1 share no common factors. 0 can be written as 0 over 1. So 0 is rational. And then, for example, 5/3. That's rational. It can be written as a over b, where a and b are integers, and there are no common factors. Now you might say, well, we could also write 5/3 as 10/6. And I would say, well, yes, that's true. 10/6 is equal to 5/3, but we're not going to consider this representation when we talk about rational numbers. When I want to say, given a rational number, or let a be a rational number, you should think of it as being written in reduced form. So because we know that for every rational number, by definition, it can be written in this form where the numerator and the denominator show no common factors. So for example, if you told me that you were thinking of 4 as 8 over 2, I'd say, please don't use this representation, 8 over 2. Use this representation, 4 divided by 1. Now you may be wondering, what's a good example of a number that's not rational? And the claim, or what we're going to prove right now, is that the square root of 2 is not rational. And we're going to prove it, so that means I'm going to follow a sequence of simple steps where each step is easy to follow, and at the end you'll be convinced that square root of 2 is not rational. Our strategy is going to be a proof by contradiction. What's the first step in a proof by contradiction? Well, the first step would be, in this case, to assume that square root of 2 is rational. Right? We're going to assume the opposite of what we're trying to prove, and we're going to arrive at a contradiction. So we start by saying square root of, let's assume, for sake of contradiction, that square root of 2 is rational. What does that mean by the definition of a rational number? It means that square root of 2 can be written as a over b, where a and b are integers, b is non-zero, and a and b share no common terms. I'll just write share no common terms. Okay, so step 3 is going to be to square both sides. So we'll have 2 is equal to a squared over b squared. And then also in this step, I'm going to multiply the left-hand side and the right-hand side by b squared. So we get 2b squared equals a squared. So far, a simple sequence of steps. Step 4, well, we can conclude this implies that a squared is even. Right? A squared is equal to 2 times something, and that means that a squared is even. Now from a previous video, this implies, what we've already discussed, is that a is even. So the reason could be previous video. We know that if n is odd, n squared is odd, right? We've seen that in a previous video. So therefore, a has to be even. I mean, if a were even, then if a were odd, then a squared would be odd. We saw that in a previous video. So therefore, a must be even. Okay, well, since a is even, what does that mean? It means that a can be written as 2 times k for some integer k. And this means that a squared is going to equal 4 times k squared. Okay, so now let's see here. We have 2, remember we had 2b squared equals a squared. Okay, so that means that b squared is going to equal 4 times k squared over 2. Right? We knew that b squared, 2b squared was equal to a squared. We have a squared here is 4k squared. So therefore, b squared is 4k squared over 2. And this implies that b squared equals 2 times k squared. And this implies that b is even. Right? Because b squared is equal to 2 times something, so b squared is even. And again, by the same steps above, that means that b is even. So look at what we have written down here. In step 5, we have that a is even. In step 7, we've written that b is even. That means that we can conclude a and b share a common factor. What is that common factor? Well, it's 2. They're both even. A is even and b is even. That means that 2 divides both of them. And so that means that they share a common factor. But remember, all the way above here at step 2, we assumed that the square root of 2 could be written as a over b, where a and b share no common terms or no common factors. We just concluded from step 8 that a and b do share a common factor. So step 2 contradicts step 8. We've arrived at a contradiction, which is often written by this symbol, and this completes the proof.